Hello and welcome. Today we're going to be talking about our final installment video on the properties of harmonic functions. The property we're going to talk about, the final one, is the minimum energy principle. Okay, so let's recall we have Laplace's equation. So these are harmonic functions. And we have to develop now this notion of energy. So what do we mean by energy? I think it's best to understand U as a surface that satisfies some boundary condition, such that if you have here's our axes, and we have some set W sitting here, and it has some boundary partial W like that. There's some boundary function that goes around like that, and I'm sure you've seen me write this that picture many times now. So U evaluated on the boundary of our set is equal to F, and this is of course a given function that we've found. All right. So we know that there exists a surface that satisfies the Laplace's equation that can meet that. It's a unique surface that is guaranteed to exist. But we have to have this notion we have to think of this function basically as a surface that's stretched across the F frame, like spandex. It's sort of bent into the F boundary condition, and the interior is the stretched fabric in equilibrium. And in fact, that is a good model for what the Laplace's equation surface looks like. If you were to take some complicated frame on the boundary W that maybe goes up and down or whatever it does, that frame would be F, and you were to anchor a piece of spandex onto that frame, the interior of that surface, the interior points connected by that frame to that surface would be more or less the solution to Laplace's equation. So clearly there's stretch involved. So stretch, that means of course there's tension, and that means there's force. Tension and force are the same thing. And that means that there's certainly energy. There's energy involved in forcing the surface to comply with the boundary condition. So the question is, how do we actually compute energy? How do we actually define that? So to do that, what we have to do is let's think back into the 1D case of the wave equation. What we have, of course, in equilibrium. Well, let's not go with equilibrium, but rather just talk about the forces involved. And we know that at any 2 points, we can define the slopes of those functions. The slope of that so this, of course, is some sort of string. And those slopes, of course, are going to be the forces. So here we're going to have a downward force in this direction and an upward force in that direction. And the difference between those true forces, of course, is the net force. It's going to be this plus that, which should equal 0 in equilibrium. And we know that the force is going to be, we usually call it phi, which is going to be negative t partial derivative of u with respect to x. Okay, so it's another negative gradient law, right? Likewise, the force in 2D, so this is the 1D force, is going to be a vector field now, and it will be negative t times the gradient field of the surface. So this is what we're going to use here to talk about forces. So we know, of course, that if we're going to start at 0, a gradient, and bend the surface to the final configuration. If we're going to do that final configuration, we'd expect the work to be done, or what we call the energy, is going to be the double integral over that interior set of the gradient vector in magnitude squared. But because we're talking about energy, we always add that 1/2 there. And this idea comes from that of a spring. The spring, of course, is negative kx. That's equal to the force. Of course, the work being done is the integral from, let's say, x0 up to x1 of negative kx dx. Now, we might want to take a negative if we're actually putting work onto the spring, so that makes it positive. And what we end up with, of course, is that it's going to be kx squared over 2. That's where that 1/2 from, and we evaluate it at the initial, at the final position minus the initial position. So the idea here, of course, is that it's that 1/2 quantity squared framework, or that functional form, that informs how we define the energy in this particular case. So that's one argument for why we define energy to be this, and we actually call this E of U. Okay, so if that's what we consider to be the energy in this fabric, this stretch fabric, if you can think of this as basically like a stretch spring, but the spring is activated by changing the magnitude of the slope of the function everywhere, rather than to just move a spring, because the spring is literally integrated within the fabric itself, because the fabric is stretchy. Okay, so with this said, now we want to go on and talk about the energy principle. The minimum energy principle is as follows. Let U be a harmonic function, and it's satisfying the boundary condition on the boundary of our set. So it's harmonic on W, some interior set. And again, I'll draw this one more time. We have our set W, we have our boundary, and we have our function sitting over the top of it like that. So what we want to do now is say that we're going to define this, that basically, and then let H be any other function, so that H evaluated on the boundary is also equal to F, all right? So any other function, what we mean is that H may not necessarily be equal to, it may not be the Laplacian function. Okay, then the following is true. The energy of U is always less than or equal to the energy of any other function satisfying the same boundary condition. And with equality, only if H is equal to U. Okay? So this property that the harmonic functions carry the least amount of stretch. Harmonic functions are least stretched. Minimum energy. Their minimum energy compared to all other functions with the same boundary condition. Okay, so that's just another way, and I use that term least stretched in the more colloquial way of basically we're bending these stretchy fabrics over a material. If the surface has more bends in it than the Laplace's solution, it will have higher energy. In fact, there is no surface that has lower energy than the Laplace's solution to the harmonic function. That harmonic function always has less energy in it. All right. Now we want to do two things in this video. First, we're going to prove it. Prove the theorem, the min energy. And then, of course, we also want to, we're actually going to look at an example. We want to look at an example just to verify that it is and truly, in fact, lower energy if you look at a harmonic function than some other function satisfying the same boundary conditions. So to prove it, we actually need, so in many of the other videos, you notice that our proofs weren't really that complicated. A lot of them were just direct calculations. For this one, actually, we do need some extra tools, so it's actually kind of tricky. But it won't be too bad. What we're going to use is, we need one thing. We need something called Green's first identity. So Green's first identity is something that you may not see in a normal vector calculus course. It's not too hard to prove. Sometimes it's asked as maybe a challenge question in a homework set or something, but it's definitely not something that you normally see very often, unless, of course, you're studying PDEs. Then it shows up. So Green's first identity is as follows. Is if you let f of x comma y and g of x comma y, actually, let's use different letters here. We'll say it's going to be, we'll call it h of x comma y, and then g of x comma y, be any functions, as long as they're differentiable and all that good stuff. And then we say the following. Then we have the gradient of h dotted with the gradient of g, dA, and we're going to integrate over the entire set W. We can write it as follows. It's going to be the integral around the boundary of our set times h times the gradient of g dotted with the normal to the boundary, ds, minus the double integral over the interior of the set of h times the Laplacian of g dA. So let's look carefully at this. You'll notice that what this really looks like, this is actually integration by parts in four, I should say just four double integrals. So that's a pretty interesting identity, that basically what we're looking at is an integration by parts formula. Okay, so it turns out that in the calculation of minimum energy, we're going to see this. And instead, what we're going to do is we're going to replace with this. So it won't be too hard, the proof, once we have this. So I don't want to go into detail about why this is true. What we're going to do right now is just use this identity. We're going to assume that it's true and just use it and get done with the problem. So we don't have to think too deeply about the details of this formula. All we need to know is that when we see this, we're going to replace it with that. Okay, so let's go on. So what we're going to do, though, okay, is that we have, so we're going to be given, we're going to be given U, we're going to be given H, right? And we know that U satisfies Laplace's equation. H does not. Okay? Now, what we want to do then is say that we also want to say that U evaluated at the boundary of our set is equal to F, and H evaluated at the boundary of the set is also equal to F. Okay? So they both satisfy the same boundary conditions. All right, but what we want to do now is actually say that H is equal to U plus a new function called psi. Okay? So psi is literally just the difference between H and U. Literally, we can write it this way. Psi is equal to H minus U. Okay, so then what we can do is say, and note also, this is really important, that psi, when you evaluate it at the boundary, is going to be equal to 0. All right, and that's just a simple fact that if both functions if you're taking H minus U, if you look at their value at the boundary, it's going to be 0 because you're taking the difference of the two. So that's a really important fact. All right, so with these things, so this is going to be our proof right here. So what we want to do now is say that we want to look at E of H and figure out what its value is. But now we're going to express EH now as U plus psi. So you can think of psi actually as maybe a deviation from U. It's how far away H is from U, right? And we know that's going to be equal to 1/2 the double integral over W of the gradient of U plus psi in squared magnitude dA. All right, well, let's just get started with calculating this. That's going to be 1/2 the double integral over W of the sum of ux plus psi x quantity squared plus uy plus psi y quantity squared dA. And we can continue expanding this. Got to remember that 1/2. And then we're going to get a ux quantity squared plus uy quantity squared. And again, all I'm doing here is just multiplying all this stuff out here, okay? So when I do that, and then I also have two pure squared terms here, which is going to be psi x quantity squared plus psi y quantity squared. And then we're going to have those cross terms. We're going to have ux psi x plus uy psi y dA. Okay, so we'll write dA there. All right, so in order to note, though, that this, of course, looks like the energy of U, and that looks like the energy of psi. So again, we started with the energy of U plus psi, and now we can write the following. So the energy of U plus psi is equal to the energy of U plus the energy of psi plus a few cross terms. So we have a 1/2 here. Oh, you know what? I forgot. There needs to be a 2 on those cross terms because, of course, when you do the cross multiplication, you're always going to accumulate 2. So what we're going to do is we'll take off that 1/2 and write plus the double integral over ux psi x plus uy psi y dA over my set W. Okay, so now we're getting there. But if you look at this, this looks, of course, like a dot product of two gradients as follows, right like that. All right, so we should be able to work this out and figure out what this whole thing is. So let's actually notice that this, of course, is what we're going to identify as actually, this is the Green's first identity. So let's just work on this one term here. What we know is we have grad psi dot grad u dA. Well, we can write this now as the following. We can write this as the flux integral with psi times the gradient of u dotted with the normal vector of the boundary set, ds, minus the double integral over w of psi times the Laplacian of u dA. So let's look at a few facts. The first fact we know, and this came from prior in the problem, is that psi, when evaluated at the boundary, is always 0. Notice we have an integral that's wholly over the boundary. That means this whole integral is also 0. 2, another fact. We know that the Laplacian of u is 0 by definition. That means this integral as well is also 0. And that means that whole term is equal to 0, and it means that we can throw that out completely. And again, it should be noted that this set of cross terms, again, all this stuff that's up there, sitting up there, the set of cross terms integrates to 0 because of facts 1 and 2. Okay, so you need them both. We need u to be a solution of Laplace's equation, and we need our correction factor, or our correction term, to have 0 boundary condition. So we have both of those, and so we're fine. Okay, so what that means altogether is it means that E of h, this function that we want to determine its energy, if we break down h into u, the Laplacian, which is a unique function, plus psi, that correction term, we can then break the energy of h into two pieces. There's the energy from u itself, plus that energy from the correction term, or the deviation term there, right? Also, note that e for any function is always greater than 0, right? Because we're summing a squared, we're integrating over a squared quantity. These are always positive quantities. It's a vector magnitude. So it must be that EU is greater than EH, because EH, of course, is equal to EU plus something else, the energy in that correction term. So this proves our theorem, our minimum principle. Min energy is proved. So we can check this box that we have it. All right. So now that this is proved, what I want to do now is understand, let's just go through an example of why this is true. Let's talk about a specific example. So I'm going to use my favorite example, one we've used in many of these other videos, of the hyperbolic paraboloid. Let's compute the energy in this thing, and we're going to do it on the unit disk. So the unit disk, we can do that. So of course the function, if here are the axes right here, and we know the function goes up there, these parabolas, and it makes that shape right there. And there's the unit disk, which I'll put a little bit lower down there. We also can say that u on the disk, or I should say on the circle, is going to be equal to cosine of 2 theta. And so you can find that by plugging in the polar coordinates to it, that's truly what the boundary condition is. Okay, so with that set now, what we want to do is we want to compute what the energy is. So of course we have to compute the gradient vector, and that's going to be 2x and minus 2y, and then we take the magnitude of that, and we're going to get 4x squared plus 4y squared. We can switch to polar and call that 4r squared. So this is polar, in which case we can write the energy of u as 1/2 the integral over the disk grad u in magnitude. I can write that now in polar coordinates as 0 to 2 pi times 0 to 1, because we're on the unit disk, times 4r squared. And of course we take our dA, in this case is going to be r dr d theta. So we should be able to get this straight away. What we have here is 2 pi over 2 times 4 times r to the 4th power over 4. The 4's cancel there, and we're evaluating at 0 to 1, and we get that the energy in this, so those 2's cancel as well, and then the energy in this thing is equal to pi. Okay, so the energy is pi on this surface. So now what I want to look at, we're going to do a correction now. So I want to do now, I want to deviate the surface. Again, I'm just checking to see if I do make a change to the surface. So I'm going to say let psi equal x squared plus y squared minus 1. So note that psi evaluated on the circle is going to be equal to 0. And that's because x squared plus y squared minus 1 is equal to 0 on the circle, right? Because the circle is defined as x squared plus y squared is equal to 1. Okay, cool. So let's do that. Let's take u, and we're now going to add on our correction term, and we're going to get x squared plus y squared. Oh, sorry, undo that. It's minus y squared. That's the hyperbolic paraboloid. And then we're adding to it this additional bend to the surface, which is going to look like a paraboloid. In which case we're going to get 2x squared. And notice the y's will cancel. 2x squared minus 1. All right, so now what we're going to do is compute the energy of u plus psi here. Right, and that's going to be the double integral over the disk, w. We'll call it w here. And then now we have to take the gradient. So the gradient of u plus psi is going to be equal to a 4x, comma 0. So when we take the magnitude of that, it's going to become 16x squared dA. Well, to do this one, we're going to have to take r, note that x is equal to r cosine theta, right? And that means that x squared is equal to r squared cosine theta squared, which is equal to r squared. Oh, I forgot the 1/2 on my energy. Okay, we'll put that up there. All right, so then we're going to do the trig identity 1 plus cosine 2 theta there, like so. Okay. Oh, you know what? We forgot one thing though. It's no, we didn't forget anything. We have it all here. So we have dA there. All right, so now what we have to do is write out this integral and just sort it out. So we're going to use polar coordinates. So I see we have that 16 and that 2. So I think it's worthwhile to turn this into an 8, 16 divided by 2. And we're going to take the integral from 0 to 2 pi, and the integral from 0 to 1. And then what we have here is an r squared over 2 times r squared over 2 times cosine 2 theta d. And then finally, what we have to do, of course, is have that dA is equal to r dr d theta. Put that there. So we have an r, a dr, and a d theta. And now we're ready to go with this integral here and compute all of this there. So I see we have these 2's. Let's just factor them out. And we're going to have a 4. And then we're also going to have an r. So we're integrating from 0 to 1, and then we're going to have an r cubed plus r cubed cosine theta 2 theta. So I might as well do the dr integral, and 0 to 2 pi, and then we're going to have an r to the 4th over 4. Remember the 4 out front, plus r to the 4th over 4 there, times cosine of 2 theta. We're going to evaluate at 0 to 1. And then we're going to have, and then notice, of course, that the 4's are going to cancel. And we're left with 1 plus cosine 2 theta d theta. And note that that's going to be a 2 pi plus the integral of 0 to 2 pi times cosine 2 theta d theta. And note, of course, that that is going to integrate to 0 because it's a cosine. So our energy is 2 pi. So remember, the energy of U by itself was equal to pi, and the energy of U plus psi was equal to 2 pi. Well, I don't know any other way to say this, but that's clearly true, that that the energy of our harmonic function is lower. In fact, it's half the size of the corrected function. So again, this is just a bunch of double integrals that we're doing here, but again, it's just verifying through a set of concrete steps what the theorem had predicted, and we have confirmed in this particular case that yes, the theorem is true, but it turns out, of course, by the proof that will always be true. Any harmonic function that satisfies a specific boundary condition, any perturbation you make to it, any distortion you make to that surface that adheres to the same boundary condition, you can only increase the energy. You're only distorting or stretching the surfaces more than it wants to be at. And so it truly represents that equilibrium minimum energy point. So I hope you enjoyed this video, and this is the last property we're going to cover in this series. It's a really important property. Thank you very much.